Hello everyone, my name is Mao-Lin. I come from Arizona State University. Today I'm very happy to present our work, GTT, guiding the tensor train decomposition. And this work is done with my advisor, Dr. Candan, and Dr. Sapino from Arizona State University and the University of Turin. And this work has been supported by the NSF Fund and the European Commission grant. And also, our experiments for this paper were conducted using an SF testbed chameleon. So let's begin. So this is today's online. First, I will introduce our motivation and the challenge we are trying to solve. And then we will introduce our main idea, which is GTT guiding the tensor train. And finally, we will present our experimental results and the conclusion. So the motivation of our work is that, as we know, the demanding of searching, querying multimedia data is everywhere. The multimedia data include image, video, and all of them we can consider as a high-dimensional array, which is we can call it tensor. To analyze this tensor, a lot of the approach, like the tensor decomposition, has been proposed. For example, we have CP decomposition and we have Tucker decomposition. So basically, this tensor decomposition will factorize the original input tensor to vector matrix with the core tensor. So for example, in CP, after CP decomposition, we have multiple vector matrix and also a diagonal core. And for the Tucker, we also have, after the decomposition, we also have the multiple vector matrix and a dense core tensor. So however, these two approach has its potential issue, which is we have the exponential memory growth with the number of the tensor mode. Sometimes we call it the cost of the dimensionality. So to resolve this issue, the tensor train decomposition is proposed. So basically, the tensor train decomposition will factorize the original input tensor to a sequence of the 3-mode core. And this sequence of the 3-mode core can be approximated to represent the original input tensor. So here I want to give a quick review about how tensor train decomposition works. So basically, once we got the raw data in the tuple style, like for example, for this data set, each row represents one data instance, and each column represents one mode. We can also call a feature. So once we have this data set, and if we apply a suffix encoding scenario like the one-hot encoding, we can generate a related tensor. So in this example, in the data set, we have 3 modes. So we can generate a 3-mode tensor. And the entry in this tensor can be will indicate the presence of the corresponding tuple in the data set, and 0 indicate its absence. So if we start applying tensor train decomposition for this 3-mode tensor, the first step we will do is that we will have to decide TT decomposition order. In this example, we use mode 1 as the first mode we want to decompose it. And then we select mode 2, and finally we select mode 3. And the second step we need to do is we have to decide TT ranks. So in this 3-mode tensor, we have 4 TT rank, which is R0 to the R3. And this R3 will represent the number of rank we want to use during the tensor trend decomposition. So after we decide these two setup ahead of the decomposition, the first step of the decomposition will be looked like this. First, we will unfolding the input tensor at the mode 1, because the sequence we decide ahead of time, the first mode will be the mode 1. So we base on mode 1 to do the unfolding. So after unfolding, we can get the 2D metric. And then we will apply the SVD decomposition with this unfolding metric. And also the target rank of this SVD decomposition will be the R1. Again, this R1 will be decided ahead of the time. So after this SVD decomposition, we can get the U metric, S metric, and the B metric. So this is the first time we apply the SVD decomposition to our unfolding metric. And then once we got the S metric and the B metric, we will multiply them and then apply and then we will reshape this metric to another reshaped metric. Here is the metric C. Once we got this reshaped metric C, we will apply the SVD again with the target rank R2 to generate U prime, S prime, and the V prime. So once we done this above step, we will reshape the vector metric we got from the previous SVD decomposition. So for example, the G1 here is a 3D tensor, which is reshaped from the U metric when we apply the first SVD decomposition. And the G2 is the U prime metric, which is we got this U prime from the second SVD decomposition. And the last core, G3, is the reshape from the S prime and multiplied by V prime transport. So once we got these 3 cores, and these 3 cores we call the tensor trend representation, which we can also call it the TT format. So this is the basic idea about the tensor trend decomposition. However, there's a challenge we have to face, because as we know, the order of the decomposition in the tensor trend decomposition, we need to decide the order ahead of time. However, this order of the sequence affects the final decomposition result. Here I use an example. And this data is come from the Wisconsin breast cancer data. I picked 3 features, which is ID. Mode A is ID. Mode B is a diagnosis. And mode C is the radiance. In these 3 mode tensor, actually we have 6 possible decomposition sequence. And then we compute the related F-norm difference between original tensor and the reconstructed tensor from the TT format. So here, the y-axis is mean the related F-norm difference. The lower the better. That's mean because we have lower error. And as we can see, the best result we can get is 0.77, which if we apply the sequence ACB as our decomposition order. And the worst result we can get is 1.11, which we apply the CAB as our decomposition order. So as we can see, there is about 25% difference if we select the different TT decomposition order. So our goal is that how can we select the mode sequence for the TT decomposition, and this selection can achieve a better decomposition result. So if we want to, if we formalize our problem statement, that would be look like this. So given the d-dimensional tensor X, which we have d dimension, and each dimension has this one length, and we have a target decomposition rank R. So our goal is to find a permutation from all the possible decomposition order, and this selected permutation can minimize the approximation error when we do the TT decomposition. So here we propose GTT regarding the tensor train decomposition. In this work, we identify significant relationship between the data characteristics and also the accuracy of different tensor decomposition order. And based on this data property, we propose 4 selection strategies. We propose based on the number of the parameters, mutual information, and the inverse entropy. And finally, we further propose a hybrid strategy which combine these 4 selection strategies to achieve better order selection. So the first part of our work is that how can we define the data characteristics? So we consider each tensor has its own data characteristics, and we can also say has these one features. So because once we got our data, actually there are three different kind of representation for the data set. The first one is a tuple style, as we show in the first graph. So in this tuple data set, for each mode, we can compute its mode entropy and its mode length. And the second representation of this data could be the tensor. As we mentioned before, the tensor can be generated from our raw data set. So once we got this tensor, we can compute the tensor density as an other features. And the third representation for the data set could be the pairwise information. As we know, the tensor train is a sequence of the core to represent mode core. So the relationship between two modes has its significant meaning. So we want to extract the pairwise information from that. So for the pairwise information, we can calculate conditional entropy and also the mutual information. So we want to use this data property as its feature to help us to identify whether this tensor has any kind of preference. And this preference can help us to select suitable strategy to decide its decomposition order. So in addition to this raw data property, we further to compute their average to show the scale of this feature, and also the absolute and relative standard deviation to indicate their discriminative power. So the first selection strategy we propose, we call it GTT-NP, which will based on the number of the parameters to decide the decomposition order. So the idea of this approach is look like this. So the picture I show is the process of the tensor train decomposition as we show in the previous slides. So when we apply the SVD to our unfolding metric and also the reshaping metric, actually we can see in this decomposition, the number of parameters we need to solve is depend on the size of the U metric, S metric, and the V metric when we apply the SVD decomposition. So we want to use the sum of the number of parameters during this SVD decomposition and use this value as an indicator to decide how can we select the order. And this formula can be easily generalized. Once we have the number of parameters for each order, so we can pick the order with the least number of parameters. Notice that this process is done before the tensor train decomposition. So we didn't introduce extra overhead for the TT decomposition. And the second selection strategy is called GTT-IE, the inverse entropy. So the basic idea of this GTT-IE is that given a data set, for example, in this figure, we show a data set with the tuple or style. So for each mode, we can calculate its entropy. Here we use H, capital H, to represent the entropy of the mode. So in here, we have 3 modes. So we have H1 to the H3. So we will sort this mode based on their mode entropy descendingly. So here, the mode 3 has the least mode entropy. So the mode 3 will be picked as the first mode to do the decomposition. And then we pick mode 1 and mode 2. And the third selection strategy we call the GTT-AMI, which is average mutual information. So again, if we have the raw data set in the tuple style, so we want to abstract the pairwise information between different modes. So we first compare the mutual information within this mode. So in this example, we can see the mode 2 has the path to the mode 1 and the mode 3. And the path to the mode 1 and the mode 3 has 2 mutual information. We calculate the sum of the mutual information for each mode. And then we pick up the mode which has the largest sum of the mutual information. So in this example, M2 has the largest sum of the mutual information. So it will be the first mode we do the decomposition. And then we have M1 and M3 to choose. Here we randomly pick one as our decomposition mode. And the last one is the PMI. So again, we can compute the mutual information within each mode. And then we can enumerate all the possible sequences. And each sequence could be represent a path. And we calculate the sum of the mutual information in this path. And finally, we'll pick up an order with the least sum of the mutual information. So the experimental result we want to show, we used 15 datasets from the UCI machine learning repository. And from this data, we randomly select 3 to 5 more tensor instances. And each instance has 100 samples. And we use the target range 3 and 5. And the way we evaluation is that we use the ARB, which is the average decomposition performance of a uniform order selection. That's mean, given the tensor, we enumerate all the possible decomposition order and compute the average of the reconstruction error and also the relative average ranking. as the result. So we compare our approach to this ARB selection. So first, we compare the relative average ranking, which is the lower the better. So we list all the results for the individual selection strategy. So as you can see, the different strategy work well for the different data set. So that means there's a no one for all the optimal strategy for the tensor trend decomposition. So how could we do better? So this is why we want to further propose the hybrid strategy. So the GTT hybrid means, as we mentioned before, we consider a tensor instance has this one data feature. So once we got this feature, actually we can train linear SVN classifier for each selection for each selection strategy. So for example, we have PMI, NP, and IE selection strategy. And we train, and each of them has this one linear SVN classifier. And once we got the data set, we will pick the strategy that has the largest margin from the corresponding separator. That's because the data set can be separated by this given separator. So we use the related strategy to do the order selection. So once we have this hybrid strategy, here we list the average reconstruction error, rate of the improvement against with the ARB strategy, and also the average decomposition time. So here we can see the hybrid one can, first of all, the hybrid one can achieve best performance in terms of the average reconstruction error, the lower the better, and also the rate of the improvement. And for the decomposition time, because we only select the order for the TT trend decomposition, we didn't change the mechanism in the TT decomposition. So the decomposition time will be not affected by our approach. And the second part of our result is that we present the percentage of decomposition with better than and worse than the rank of the decomposition returned on the average by the ARB strategy. So again, we can see the hybrid one can achieve the best performance within this selection strategy. So the conclusion is that we proposed an approach for guiding the tensor trend in selecting the decomposition sequence. So basically, we leverage the various data features to identify an effective order strategy, like the number of parameters and the mutual information and the entropy. And based on that, we propose 4 order selection strategy, and even we propose a hybrid approach to combine all of them to achieve better decomposition selection. And this is my presentation. Thank you very much.